This is Joe Barr, and I'm going to talk about home price index, a machine learning approach that's work was done while I was at HomeUnion for several years. The work was done in 2016. It was published in 2017 in World Scientific. You can actually grab the paper there. It was a bipartite collaboration between HomeUnion and the University of Southern California Lusk School of Real Estate with Professor Chris Redfern. And then I had a team there at HomeUnion of several capable data scientists that we together put together the both valuation, the AVM, and the home price index. A bit of a jest, real estate is an important part of our economy. And in case you didn't know that, you probably have at least heard of the real estate crash of 2008. Just tells us how important it is part of the economy. It's about, I think it might be off by a fraction of a point, but it's about 18% of our overall GDP. Real estate, everything, including construction, transaction, financial services, everything that has to do with real estate. Here we go. It's between 15 and 18% of the GDP. There's some numbers that are gonna overwhelm you. Building 1,000 single-family homes creates 2,970 jobs, generates $162 million in wages, $118 million in business income, 111 probably million in taxes and revenues for the state. There were 115 million occupied, well, approximately, of course, occupied housing units in 2013. That's according to the American Housing Survey. There are over 700,000 new constructions. That's according to Census 2015. There are over 6 million construction workers. Again, according to Bureau of Labor Statistics, 2014 numbers. Over 5 million homes sold in 2015, according to the National Association of Realtors. There are 2 million active real estate agents and 86,000 real estate brokers. One of the components of real estate transaction is the idea of valuation. What is a house worth? Houses, unlike cups of coffee at Starbucks, are not sold very frequently. So, or they're sold infrequently, I should say, and also certain areas are not sold very quickly. So it's hard to tell what's a house worth. And there are a variety of methodologies designed to help home valuation. One of them is statistical automated valuation models, or AVMs. These are statistical techniques to approximate the value of a house. And the other one is the trusted real estate appraiser, where an appraiser comes in with a notebook and takes notes about the house and sees all the houses that were sold in the area recently, and based on those factors, they make an assessment of what is the house worth. I'll focus on the automated valuation models. The automated valuation model, AVM, is a service that can provide real estate property valuation using mathematical modeling combined with a database. So we have those two elements. We have the data, we have historical sales, details about the houses sold, how much they were sold for, when they were sold, and so on. And then we have a formula that estimates the value of any house. Most AVMs calculate a property's value at a specific point in time by analyzing values of comps, comparable properties, what's real estate known as comps. AVM is based on hedonic alone. Hedonic is what economists refer to as all the information available about the product. The specific condition of the house is generally unknown. And that's where perhaps the appraisal may come in, or home inspection. But AVM is blind, doesn't actually go and visits the house. Much like consumer credit score, multitude of AVMs are available in the market. You've probably heard of Zillow. Hedonic local random effects, high dimensional regression, and boostings are two common AVM statistical techniques. Economists or econometricians prefer the former, and people in modern statistics, machine learning, prefer the latter. For example, both CoreLogic and Zillow using the boosting model framework to produce estimates, and that's well documented. You can actually go to, if you have to dig a bit, but you'll find the papers supporting, or white papers supporting their methodology. Issues with AVMs. It's well, you know, if you live in a condo and there are 200 homes just like yours, and they're sold on a fairly frequently basis, then you would probably know fairly well what your house worth. So if it's a cookie cutter neighborhood with lots of identical home sales, then you should know the value of your home. But in reality, many situations don't fall under that particular paradigm. And homes are different. They may look similar or even the same construction, but they occupy different spaces on the ground, and sometimes the way noise travels and the direction of winds, prevailing winds, may affect the value of the home, make it more desirable for one reason or another. So spatially and temporality of data plays a significant role in building valuation models. Lack of spatial temporality coverage hinders on models' goodness. And then the hedonics. So what's hedonic? A square foot is an example of hedonic. Home characteristic itself tells part of the story. For example, upgrades could only be discerned upon inspection. So upgrades only become an hedonic after you have inspected the house, but up front, it's not square footage, number of bedrooms, bathrooms, so on. It's part of the hedonic information about a house. Real estate appraisal, property valuation or land valuation is the process of developing an opinion, and I italicize opinion on purpose, of value of real property. That's from Wiki. And also from Wiki, real estate transactions often require appraisals because they occur infrequently and every property is unique. And that just amplifies what I said earlier. And the person expressing the opinion, that guy over there in the picture, is called the appraiser. And most of you have sold both houses and met an appraiser, so you know what I'm talking about. Standard AVM methodology, and that's regardless of whether you're using boosting or hedonic local regression. All the transactions that you take into consideration should be considered as arm's length home sales. That means that the transactions like grandma selling a house for $100 to her grandchild is not considered as arm's length and should not be included in the process of valuating homes in the neighborhoods. Data cleaning must be done to ensure that those kind of non-arm's sales, foreclosures, and so on, are not included in the data set. Then a pending rich feature set like socioeconomic points, POI, point of interest, and much more like Boolean if home is less than X feet from a major busy highway. The noise factor, as I said before, could be also an airport and so on. The specific features are often proprietary. That's certainly the case in the model that we have developed at HomeUnion a year and a half ago. So, application of gradient boosting with appropriate tuning parameters is used to commonly standard in the market for AVMs. And then the post-processing is done to ensure baseline quality of outputs. So the proprietary part here are the features and the post-processing. And with the modeling, the proprietary part may be setting up the shrinkage parameters and some other parameters of the data, depth of trees, number of nodes per leaf, and so on. So think of a home, and home has value every quarter, although it's not necessarily sold every quarter. So we have a time series of values. Most of them are unobserved, they're only inferred. And those are presented by a graph over time. And here you see the median sales index of the Metro LA on the right-hand side. And obviously the supply and demand law, the law of supply and demand, governs the valuation, but it governs it in a tricky way. So that's where the complexity comes in. Since I live in Southern California, we like to give examples: Santa Monica and Pasadena. And some people outside Southern California recognize those names. We know you probably heard that Santa Monica and Pasadena are both very desirable and land constrained. That's it. No more homes either in Santa Monica and Pasadena. Santa Monica has the ocean on one side, and Pasadena has the mountains on one side, and that's it. So the values in those two towns increased at a significantly faster rate than those in the Inland Empire. Inland Empire consists of the towns like Riverside or San Bernardino, where there's large tracts of land. So they're not land constrained as those two that I've mentioned. And the home price index, or HPI, is a tool that measures home price as a function of time. Rather idealized, but in principle, that's what it is. And an naive HPI, still used fairly commonly, is constructed by aggregating all sales in some geography, a metro, and then taking median or mean or something. So median per town or per zip code or something, and then you measure it over time, and you have your time series. And in fact, the National Association of Realtors, the NAR, follows that method. Here's a bit of a history. I'm going to skip ancient history. Price index is an old idea, preceded Adam Smith and the genesis of economics. But the first landmark concept was in 1963 by Bailey, Muth, and Norris introduced the concept of repeat sales analysis. So instead of just looking at the sale, you're looking at the difference, at the bump in valuation of a house as it's sold over time, repeatedly. And then the implementation was done in the 80s by the late Carl Case, that he implemented that methodology. By the way, it's a sophisticated sort of regression. You regress over the increase of values. And then in the late 80s, the Case and Shiller Index was developed. And in 2013, CoreLogic has acquired it. Okay, there are a lot of price indices that some of you may be familiar with. There's the Producer Price Index by the BLS, Bureau of Labor Statistics, Consumer Price Index, Commodity Price Index by the World Bank, and so on. And then we have our own price index down in the bottom. There is a depiction, if you see the picture on the right, of the median price index of 328 zip codes in LA. You'll see how the graphs deviate quite a bit, especially moving from 2005 or 6 onward. There's a huge disparity between some of the graphs. Tells you that maybe the median home price index is not stable. So we're going to talk about our methodology next. The median I already talked about, and repeat home sale index. Those two have big drawbacks, and that's why we developed ours. The median home price index simply only takes into consideration those homes that were sold at that time for one reason or another. So the actual valuation is not captured adequately. And the repeat home sale, the problem is you have to recalculate, go back in time, and continually fix, quote unquote, the price index. So those two have big drawbacks. So what did we do? Well, we looked at every house in the US. There are about 110 million houses. You see those big numbers there. And then we estimated their value quarter over quarter. There are about 65, actually 67 quarter. We started 2000, as you can see, ended up the last quarter of 2016. So we have 67 quarters, 110 million houses, and you end up with that gargantuan number. Actually, I only took 65. There you see the 6,500,000,000 and so on, based on 65 quarters, but doesn't matter, just add another 200 million. So we built a model, a valuation model for every quarter for every house, and then we aggregated them, and then we ended up with a price index, and then we can roll it up by the house. Well, that's how we build it, but we can roll it up to the zip code, we can roll it up to a neighborhood or some other geographic entity, and end up with a fairly smooth looking cohorts, as you can see on the blue graph on top. And then if you cohort it, you get a fairly nice and smooth time series. The problem that we encountered was that of scale. We had to build lots of models. If I remember correctly, it was 6.5 billion models, so a big number of models. We had limited hardware to work with, so we had to do a lot of divide and conquer and make some compromises, as it were. But it worked. So we ran it for a few weeks, and at the end, we had the home price index. And everybody, I'm sure, has an opinion on how to do that and how to optimize hardware. So here's a summary, and you can go and do it yourself if you so choose. Of course, you need to have the data, which is always a big challenge. So using valid sales, these are what I mentioned before, the arm's length sales. Build a gradient boosted regression tree model for each quarter, for each market. Actually, okay. You build it for each quarter, for each market. A market should be quoted, because what do you mean by market? Because you're building it for each house to estimate the value of a house. So using valid sales, build gradient boosted regression tree model for each quarter, for each market. To remove seasonality effect, use LOS, that's locally weighted scatterplot smoothing technique. And then form an index by rolling up property indices to desired geography. We did it both neighborhood and zip code. A neighborhood that those defined by either those that are established by the cities, Boyle Heights neighborhood in LA, or Lincoln Park in Chicago, and so on. Or there are third-party providers that map up neighborhoods. So, and then we just normalize it, and behold, the index. I'll use the next just couple of minutes to tell you about gradient boosting. It took me a long time to learn it, so I don't think that you'll be able to learn in a few minutes. But the data always starts with ordered pairs. So you have a vector X with P components and a tag Y, and Y is a long continuum, some number. And the algorithm implements many weak learners. These are fairly shallow decision trees, and you can control how shallow they are by some purity metric. You can think of Gini index or Shannon entropy or something like that. And then you focus on those examples that are hard to predict, and you continue the iteration until you have you reach stopping criteria, in which case you stop and you roll it all up. You take some sort of weighted average over all the leaves, and this gives you the model. So here you can see a bit of an output of a tree, and then how it translates into the geography, how the partition of the map is being done. Now, these are always rectangles. That's the nature of the beast, using decision trees. A single decision tree is inadequate because it tends to overfit. Even if you prune it, you might have problems with that. It's also sensitive to data. So single decision tree is not a good idea. And that's why we chose boosting. That's why the industry has selected boosting as the standard methodology. Question is, then we tested the home price index. How good was the index? Well, we rolled it up for certain zip codes, and we took a sample of sales, and we just compared it, and then we come up with pictorials, of course, representation. And as you can see from the picture, we were spot on several occasions. Or you can look at some standard metrics that measure errors and mean squared error, or some other metric, and then measure the quality of the index against that metric. So we've done that. And then I was curious to know, are there any places we're doing better than others? This is a map of LA, by the way, or the greater LA area. And we noticed that we're doing fairly well most of the time, or most of the places, I should say, with some areas that we aren't doing so well. And the green areas we're doing well, and the red areas not so well. And it will jump right out that in Malibu we're not doing so well. And I think I know why, because Malibu are places where rich people live, and the number of transactions is fairly low. And for some reason or another, we're not capturing values very well there. Then there is a little blot in 29.6, right in the middle, where I'm doing very well. Maybe it's the Getty Center, I'm not sure. Aggregated HPI. So these are the market trends for each zip code in LA. And you see there's some noise, but overall it's fairly solid. And you can see the trend emerging very nicely from it. And then there are many refinements that are necessary in order to make it even better. For example, we need to correct for sample bias. We need to correct for seasonality and cyclical effect. For example, we know that in the winter, houses are less expensive than in the summer. And the reason is not that the prices drop. The reason is that people sell in the winter. Those who sell in the winter are those who must sell and can't wait until the summer to sell. So there's this seasonality bias. And that's it. And I'm done. Thank you very much.